I'm Carl. I'm a safety and security engineer at Codasip, and I'm going to talk briefly about CHERI and sort of software. How does it actually work, or how does it look in terms of your software? Take a normal C program, for instance, and you're trying to access memory. So you might define some form of a pointer type. In C, traditionally you could define a pointer. I mean, a pointer is an integer, effectively, so you could define it whatever you want. So, but let's take the overall, say, void star pointer or something like that, and look at a comparison between a CHERI and a non-CHERI system. So, doesn't matter what the type is, really. But say we have some form of a pointer. So on a non-CHERI system, a pointer just contains an address. And obviously the problem with that is this can be anything. And if somebody comes in and tries to attack your system, all they need to do is modify this address and they can access whatever region of memory they want, you know. You might have set your address to this, but they could change it so it accesses this. So whether this is, a direct modification into the address itself, or whether this is performing some sort of arithmetic operation in it, like overflowing in a loop or something like that. Now, CHERI, on the other hand, doesn't just have an address for a pointer. So CHERI represents pointers as something which we call capabilities. And capabilities there's a long history of this in security, but it's effectively an unforgeable token. It's just in CHERI's case, we're going to use it for memory protection. So this is a non-CHERI case and CHERI case. And in this case, this is a capability. And whereas this is an integer. So say this is, we'll take a case of 64-bit machine. In CHERI, we retain this integer portion. So say it's an address. And it's retained as 64 bits. Now, we also, in CHERI, extend this out by, depending on the format used, but typically 64 bits. And you can consider this as metadata. Now, within this metadata, we store things like the upper and lower bounds, and we store access permissions. So say read, write, execute. There are other ones, but basic level is what we do. And if you notice, these upper and lower bounds are, the question obviously is, how do you get upper and lower bounds within, a much smaller bit size than 64 bits when your address is 64 bits. So we actually use almost like a floating point representation here. It's a mantissa exponent, which means you do have to worry about alignment, but we can cover broad range of things while still only using a smaller number of bits. And in the machine itself, what we do is typically your CPU contains a set of registers. In RISC-V, this could be, you could have A0, A1, this sort of thing. So these now become capabilities. So we extend architecturally the registers inside the CPU out to the 128 bits rather than the original 64 bits. And actually, they're extended out another bit. So capabilities are 129 bits on a 64-bit machine. This additional bit is a tag bit. Now, the tag bit's sort of special. We use it to maintain the integrity of this stuff, and it's not software visible except for you can read it, but you can't write it. And if you perform an illegal operation on a capability, this will automatically be set to 0, which means invalid. So the tag's effectively a valid bit. And we store this to memory as an additional bit in the memory as well. But this is all hardware controlled, which means architecturally our registers are 129 bits, because in our register file we also keep track of this tag bit. So it means that only specific operations, software operations, instructions can be used to change capabilities. And in fact, we do have the capability as well, the ability to lock or seal, as we call it, to make the capability immutable, so that only certain instructions can operate on it, even further tying it down. And that's typically used for control flow integrity protection. So for instance, we could lock a capability or seal a capability that contains the return address to a function, so that only a branch or a jump instruction can unseal it and use it. And this protects things like return-oriented programming or jump-oriented programming attacks. So advanced attacks, but we can use this whole concept of capabilities in CHERI to protect this. And then in your code, so your C code, you'd compile as normal, actually. In most cases, the CHERI compiler is smart enough to work out it's a pointer and replace it with a capability. We have to do things a bit more at the start, because you can only derive a capability from another capability, and it has to have less permissions or rights. So yeah, on our C program, we replace pointers with capabilities. Now, we have a number of rules for capabilities. We can only ever derive a capability from another capability, but it has to have less rights or permissions. So the bounds must be less or equal, and the permissions must be equal or less. So whenever the machine starts, we have to start somewhere. So we have a program. If you think of the normal program counter, we now have a program counter capability. And this has the normal address component, but when the machine starts, we also have lower upper bounds, permissions, which are set to the full extent possible. We can use this starting point to derive a set of capabilities down from that. And then as the software operates, we reduce it further and further until you get to something like an array. So you create, array, say we have int, array of 5. We can actually keep breaking down these capabilities until we have one that literally just covers this. So anything accessing it is restricted by its capability. So rather than a pointer, this is now a capability, same as all pointers. And that's how CHERI gives its memory protection.